Welcome everyone for today's class. In this class, we are going to discuss about Hyodometric titrations and iodometric titration. In the previous class, we were discussed about redox titrations. We know what is redox titrations. In redox titrations itself, we have permanganometric titration, hyodometric titration, hyodometric titration, serimetric titration, and so on. In that series, we are going to discuss about Iodimetric titration and Hyodometric titration. In the Hyodometric titration, that is, there the iodine reactions occur. It is the branch of volumetric analysis based upon the use of iodine as an oxidizing agent is called Hyodometric titration or Hyodometric titrations. In iodometric titration, it is concerned with the titration with standard solution of iodine, whereas in iodometric titration, there is the titration of iodine liberated in chemical reactions. Therefore, in iodometric titration, we are titrating using the standard iodine solution, but in iodometric titration, the liberated iodine is titrated with the given titrant, which means that is in the iodometric titration, it is also called as direct titration of iodine solution, and in iodometric titration, the titration of iodine liberated in chemical reactions, which are called iodometric titration. Here I have given an example, that is for example, for iodometric titration, it includes the titration of iodine with thiosulfates, arsenides, stannous chloride, sulfurous acid, and so on. Here I have given an example. The sodium thiosulfate is titrated against the iodine solution, which gives sodium tetrathionate and sodium iodide. And then another one example, the sodium arsenate titrated against the iodine and it gives sodium arsenate. In these reactions, the iodine behaves as a weak oxidizing agent. In iodometric titration, the iodometry that includes the titration in which iodine involved as a result of reactions between a neutral or acidic solution of an oxidizing agent with an iodide. It is titrated with a standard solution of a reducing agent, usually sodium thiosulfate. Common oxidizing agents used in these titrations are potassium permanganate, potassium dichromate, and copper sulfate. I have given an example here. The potassium dichromate is react with the sulfuric acid and gives the potassium sulfate, and the sulfate salt of the chromium, and here the liberation of the nascent oxygen. This oxygen is react with potassium iodide and gives potassium hydroxide, and it liberates, this reaction liberates iodine, that is Hi2 molecule. So this liberated iodine is titrated with the titrant. And then the copper sulfate is reacted with potassium iodide, and it's also liberates the iodine. This iodine is titrated with the titrant. Therefore, we know what is iodometric titration and hyodometric titration. In iodometric titration, that is also called as a direct titration, because the iodine solution is directly titrated against the reactant we are taken, and in iodometric titration, the titrated against the liberated iodine. There are some of the differences between iodometric and iodometric titrations. Here in the iodometric titration, it is direct titration of iodine, but in iodometric titration, the titration we are, that is indirect titration. It is not direct titration, it is indirect titration of iodine. And therefore, here the Hi2 liberates in the reaction between potassium iodate and potassium iodide. In iodometric titration, we take here iodine is used as a titrant. In iodometric titration, iodine is not used as titrant, but potassium iodate are used as titrant with react with potassium iodide. And in iodometric titration, it is carried out in neutral or slightly alkaline solution because it forms hypoiodate ion from iodine, which is strong oxidizing agent. But in iodometric titration, it is carried out in highly acidic condition in strongly alkaline solution. Hypoiodate ion is formed. Here in iodometric titration, we use a neutral or slightly alkaline solution, but iodometric titration, so that is carried out in highly acidic condition. And in iodometric titration, starch indicator is added earlier in titration, but in iodometric titration, starch indicator is added near the endpoint because it gets decomposed in highly acidic condition. And then in iodometric titration, endpoint is blue to colorless, and then the iodometric titration endpoint is brown to pale yellow to the colorless. For example, titration of iodine with sodium that is sodium thiosulfate. And for example, for iodometric titration of sodium thiosulfate with potassium iodate, potassium bromate, and potassium dichromate. These are all some of the examples for iodometric and hyodometric titrations. And we shall discuss, and here during for the endpoint, to determine the endpoint, we are using starch as an indicator. When we use starch as indicator, starch is used as an indicator for titrations involving iodine. Starch, here the starch reacts with iodine in presence of iodide to form a blue complex. This is a very sensitive color reaction, but starch forms a water insoluble complex with iodine. Therefore, the indicator is added only at the very end of the reaction, when the color of the iodine solution fades to pale yellow. So that is in during the iodometric titration, initially we are adding the starch indicator, but in iodometric titration, so in the final stage only we are adding starch indicator. And then there are two common important sources of error in titrations involving iodine, that is iodometric titration and iodometric titration. They are, the one is the loss of iodine owing to its volatile nature, and the acidic solution of iodine are oxidized by air. So these errors are minimized. So that is, it is found that in excess of potassium iodide, the volatility is markedly increased. Hence, in all titrations involving iodine, an excess of potassium iodide is used. Also, the titration is done in conical flask and in cold solutions. And then the error due to the oxidation may be minimized by not keeping the solution containing excess of iodide and acid for long before it is titrated. So that is to minimize the oxidation. So the iodide may undergo the oxidation reaction, so that to minimize this error, so we should not keep the solution containing excess of iodide and acid for long before it is titrated. Therefore, there are some conditions to execute the hyodometric titrations. They are, so when you are doing the hyodometric titration, this titration is carried out in acidic condition only for the evaluation of iodine in reaction. And the hyodometric titration should not be carried out in highly alkaline conditions, because hypoiodate ion, that is HyO minus, is formed, which is strong oxidizing agent than iodine. For example, sodium hydroxide and iodine gives, that is sodium iodate ion and sodium iodate and water molecule. So during the reactions, iodine is evolved and it is volatile. So uh, carry out the titration closed vessel, that is iodine flask, and in cold condition should be used. And then iodine is very slightly soluble in water, therefore there is a need to add excess of potassium iodide to dissolve the iodine. That is, here the iodine is dissolved in potassium iodide like this, and it forms potassium iodide. And we should keep the flask in dark place to decrease the volatilization of iodine. So iodine is highly volatile, so that we should keep this iodine in a dark place, in a flask in a dark place. The rate of reaction between iodate and iodine ion is very slow, so sufficient time should be given for completion of the reaction. To complete the reaction, we should give the sufficient time interval. The reaction mixture is kept in dark. The reaction mixture is kept in dark place, because during reduction of iodine to iodide, uh, iodide light accelerate oxidation of iodide to iodine by atmospheric oxygen. That is given in the equation form. Here the iodide is oxidized into the iodine, so it should be avoided by keeping in dark place. That is because during the reduction of iodine to iodide, light accelerate oxidation of iodide to iodine in atmospheric oxygen. So these are some of the conditions when we are doing the iodometric titrations. That is, it should be carried out in acidic condition, and then it should not be carried out in highly alkaline condition, and then during reaction, so iodine is evolved and it is volatile. Therefore, it should be done in the closed vessel, and it is iodine is very slightly soluble in water. Therefore, it should be added excess of potassium iodide to dissolve the iodine, and then the titration should be done in the flask in dark place to decrease the volatilization of iodine. The rate of the reaction between iodate and iodine ion is very slow. So sufficient time should be given for completion of the reaction, and the reaction mixture is kept in dark place because during reduction of iodine to iodide, light accelerate oxidation of iodide to iodine by atmospheric oxygen. So these are the conditions we should keep in mind when we are doing hyodometric titrations. Here I have given an example for iodometric titration, that is a standardization of sodium thiosulfate with potassium iodide. In this titration, uh, how we are doing is dissolve accurately weighed 1.3 gram of pure and dry potassium iodide into 250 ml distilled water. Then pipette out 20 ml of solution into conical flask and add 2 gram potassium iodide and dilute sulfuric acid 4 ml. Iodine liberate in reaction. That liberated iodine is titrate the liberated iodine with 0.1 molar sodium thiosulfate solution. When the color of the solution becomes pale yellow, that is near to end point, add starch paste as an indicator. So continue the titration until the solution becomes colorless. The reaction occurs in this estimation is given. The overall reaction of this is, so iodine and thiosulfate react and gives uh, sodium iodide and so on. And this is an example for iodimetric titration, that is standardization of iodine with sodium thiosulfate. In this, first we do that the preparation of zero point 0 molar iodine solution. To prepare this, dissolve here the 2 gram of potassium iodide is dissolved in sufficient water. Then the 1.3 gram of iodine is added, and make up the volume up to 100 ml with distilled water. Then the iodine form complex with potassium iodide, which has better solubility in water. After that, after the preparation of 0.05 molar iodine solution, then we are preparing the preparation of 0.1 m sodium thiosulfate uh, solution. To prepare this, dissolve 2.5 gram of sodium thiosulfate and 0.02 gram of sodium carbonate in carbon dioxide free water and dilute to 100 ml with water. Sodium thiosulfate is readily degraded by bacteria, which uses it as a source of sulfate. So, sodium carbonate is added, which makes the solution alkaline, and bacterial activity is negligible in alkaline pH, that is 9 to 10, between 9 and 10. And then how we are going to standardize after the preparation of these solutions, standardization of iodine with sodium thiosulfate. Here the directly titrate the prepared iodine solution against thiosulfate, and iodine is mild oxidizing agent which is reduced by sodium thiosulfate and sodium thiosulfate oxidized to tetrathionate. At the end point, color changes brown to colorless. Here the equations are given here. The oxidizing agent, how it undergoes, iodine undergoes, accepts 2 electrons and becomes into the iodide, and the reducing agent, it in the reducing agent there is oxidation reaction is occurs, and it liberates electrons. The overall reaction of this is, so iodine is react with thiosulfate and gives the thionate, and there is liberation, that is removal of electron and the acceptance of electron is taking place. So therefore iodometric and iodometric titrations are redox titrations. So the here it is an example for iodometric titration, and then another one example, that is standardization of iodine with arsenic trioxide. Here, the arsenic trioxide is best primary standard for iodine solution. Arsenic trioxide is dissolved in water to give arsenous acid, which is oxidized by iodine solution. The pH should be in the range of 6 and 9. So, iodine act as a self indicator here. The reaction happens in this titration is given here. Here, the titration between the iodine and arsenic trioxide. So, apart from these examples of iodometric and iodometric titrations, uh, we have some of the estimations by using iodometric and iodometric titrations. They are estimation of iodine and estimation of copper, estimation of potassium dichromate, estimation of arsenous oxide, and bleaching powder, estimation of bleaching powder, estimation of hypochlorite, and also we can estimate by using this estimate the barium by using these type of titration, that is redox titrations like iodometry and iodometric titration. So in this class we understood what is iodimetric and iodometric titration. We know what is hyodometric titration and hyodometric titration. So this hyodometric and iodometric titration includes either direct titration of iodine solution, which are called iodometric titrations, or the titration of iodine liberated in chemical reactions, which are called iodometric titrations. And in the iodometric titration, that includes the titration of iodine with the thiosulfates, arsenides, stannous chloride, sulfurous acid, and so on. The example we have discussed the example for iodometric titration. In iodometric titration includes the titration in which the iodine involved as a result of reaction between a neutral or acidic solution of an oxidizing agent with an iodide is titrated with a standard solution of a reducing agent, usually sodium thiosulfate. The common oxidizing agents used in these titrations are potassium permanganate, potassium dichromate, and copper sulfate. The reactions occurring in this oxidizing agents are given below. So we discussed earlier itself. So in this class, you understood what is iodometric titration and iodometric titrations. So in the next class, we shall discuss about complexometric titration. What is complexometric titration? This complexometric titration is also a type of titration that analysis. So we'll discuss about the complexometric titration in the next class. Here once again we shall see the differences between iodometric and iodometric titration. So iodometric titration is a direct titration of iodine, and iodometric is indirect titration. So this is indirect titration. This iodometric is indirect titration, and iodometric titration. In iodometric titration, iodine is used as a titrant. In iodometric titration, iodine is not used as a titrant. And in iodometric titration, it is carried out in a neutral or a slightly alkaline condition, but iodometric titration is carried out in highly acidic condition. Here in iodometric titration, starch indicator is added earlier in titration, but in iodometric titration, starch is added near the end point because it get decomposed in highly acidic condition. And then in iodometric titration, endpoint is blue to colorless, and hyodometric titration endpoint is brown to pale yellow to colorless. Also examples we have discussed earlier itself. So therefore, in iodometric titration, the titration is done by using the iodine itself. Here in iodometric titration, the liberated iodine in the reaction is titrated against the titrant. So one is direct titration, is another one is indirect titration, because it is titrated against the liberated iodine.